Alright, hello folks. Today we shall be studying wave motion. Imagine dropping a pebble onto a lake. Let's imagine the surface of the lake is very still. What you would see is a wave that is created from the point where the pebble is dropped, and this wave will be expanding in a circle all the way to the shore. One important feature of this type of wave motion is that if you can think of the wave going by an object, for example, a leaf that was on the surface of the water, as the wave goes by the leaf, you will see that the leaf would rise and fall in a vertical motion as well as horizontal motion. So it will rise and fall both vertically and horizontally, but will not move from its original position and will not be carried along with the wave to the shore. What this tells us is that a water wave moves from the point of origin of creation and moves to the shore, but the water is not carried along with it. So the water acts as a medium through which the wave is propagated. There are all kinds of waves around, but we shall be focusing on two types of waves, the mechanical waves and the electromagnetic waves. So mechanical waves require a medium for propagation. So an example of mechanical waves is waves on water. Electromagnetic waves, on the other hand, do not require a medium for propagation. An example of electromagnetic waves would be radio waves, and also we have light waves. So for this part of our course, which is a course on mechanics, we shall be studying just the mechanical waves. So let's look at the characteristics of mechanical waves. So mechanical waves require a source of disturbance. They also require a medium for propagation, i.e., a medium containing elements that can be disturbed. Number three, there is also a physical mechanism. So electromechanical waves require a physical mechanism by which elements of the medium can influence each other. We can demonstrate wave motion by flicking the end of a string that is held under tension and attached at one end. And if you can imagine that you have a string in your hand, you stretch it and you attach it to one end and stretch it. So if the string is heavy enough and you flick it, you would create a pulse which would then travel along the string toward the fixed end. And this pulse will travel at a definite speed. And I can draw a diagram just to show you what I mean. So you can imagine forming a pulse or creating a pulse on a string. Let's write it this way, forming a pulse on a string. So we imagine that we have a fixed point there, and we have a string, and you can think of it this way. You are grabbing onto one end of that string that way, and you flick it down with a force F. So this is the pulse, and the pulse travels to the right with a speed V. So you can see that the element, which is the string, is disturbed and moves perpendicular to the direction in which your hand moves. So a traveling wave or pulse that is created and causes the so in this case, our source of disturbance is the flick, and the medium through which the pulse propagates is the string, and the wave or the traveling pulse is the physical mechanism through which elements in the medium can influence each other. Now I will write that if we have a traveling wave or pulse that causes the elements of the medium to move perpendicular to the direction of propagation, we call this a transverse wave. So I'll underline transverse wave. Another type of pulse is a pulse that moves along a stretched spring as below. And this particular pulse involves compressions and relaxations of the spring. So again, we can think of our hand holding onto a spring. So this will be a point of relaxation, and then we shall have a point where there is a compression and a point of relaxation. and we have it fixed to a certain point there. So the wave propagates in this direction. This section here is compressed. So this type of wave is called a longitudinal wave. An example of a longitudinal wave is sound waves, and an example of a transverse wave is a radio wave or electromagnetic wave. Some waves in nature exhibit combinations of transverse and longitudinal waves. An example would be water waves, or let's say waves on water, or we also have seismic waves. Now let's look at the pulse as a mathematical object. Let's consider a pulse at a time t equal to 0 as shown below. So we can draw a graph as shown below. This is the y-axis and that is the x-axis. And we can draw a pulse as shown with a point P, which is a point on the string. This is called the amplitude A. The pulse is propagating with a velocity v to the right. This velocity is a vector, of course. This is the origin. After a certain time t, the pulse would have moved a little bit to the right, so I'll draw this again. So the distance that pulse would travel would be v times t. Again, the amplitude is the same, a, and that point P is now somewhere up here on the pulse. We can describe the shape of the pulse by some function y of x0 equal to f of x, and this will describe the shape of the pulse at a time t equals 0. After some time t, we assume that the shape of the pulse does not change, so some element of the string at x at this time has the same y location as an element located at x minus vt sometime t equals 0. So we can write y of xt equals y of x minus vt at 0, and we can write this in general as y of xt equals f of x minus vt at the origin. So this is for a pulse traveling to the right, and we can say that for a pulse traveling left, we have y of xt equals f of x plus vt. So this function y of xt is called the wave function. Now let's look next at a traveling wave model. In this model, we shall consider what we call a sinusoidal wave. This wave will look like a graph of sine theta plotted against theta. So for example, for our sinusoidal wave, we can think of a wave that looks like what is drawn below. So we have our y-axis and the x-axis this way. This is y, so we can think of a wave that goes this way. So that will be a sinusoidal wave. So 2 points on the wave from this point to this point will be called the wavelength. So the wavelength can be considered to be 2 points from one crest to the other crest, or from one throw to the other throw. So we can also consider the wavelength to be from here to here. The period is the time for one complete oscillation. So before I draw the period, I'll write the wavelength. So wavelength is given by lambda, and then I'll redraw this again. This is again x, that's y. We draw our sinusoidal wave again, and the time from one point to the other is the period t. So from this point P to this point P is the period t. So t is the time for one complete oscillation, and the frequency f So t is equal to period, and f is frequency. This is the number cycles per second. We will see that the frequency is equal to the inverse of the period. The unit of frequency is hertz. The unit of the wavelength, lambda, is meters. That's letter M. And the unit of period, t, is seconds. We can also define another quantity, which is the amplitude. And this amplitude is given by letter A. It is the maximum displacement of a point on the medium from equilibrium. So in the case of our sinusoidal wave, this is x and that's y. The amplitude is the distance from equilibrium to the peak. So this is going to be positive A on this side and negative A on that side. Amplitude has a unit of meters also. A wave in general travels with a particular speed which depends on the properties of the medium involved. For example, sound waves travel through room temperature air at a speed of 343 meters per second. When sound travels through a solid medium, the speed is higher. Now, when we consider a sinusoidal wave of the form shown below, we can write its wave function as given. So let me draw the wave function again. This is x, that's y, and this is a sinusoidal wave. Amplitude is A, wavelength is lambda, period is t, and frequency is f. We can write the wave function at time t equals 0 as y of x 0 equals a sine ax, where a, of course, is our amplitude, and lowercase a is a constant to be determined. So at x equals 0, y of 0, 0 would be written as a sine a 0, which is equal to 0. So this is at x equals 0. So the wave function will be 0 again when x is equal to lambda over 2. So if we substitute this into the formula, or if we plug this in, we have y of lambda over 2 at t equals 0 to be given by a sine lowercase a, and we have lambda over 2. This is equal to 0. Now, in order for this to be true, that will mean that a lambda over 2 should be equal to pi, and this means that a is equal to 2 pi over lambda. So we can now write that at a certain time t equal to 0, the wave function y of x0 can be written as a sine 2 pi over lambda x. So what we are saying is we've determined our constant a to be 2 pi over lambda. Now suppose that the wave moves to the right with a speed v, then we can write that the wave function at a later time t is given by y of x t equals a sine 2 pi over lambda. We have x minus vt. So this is the wave function for a wave moving to the right at speed v at a given time t, or at a later time t, not a given time. So this is an important formula to keep in mind. This is the wave function formula for a traveling wave moving to the right at a speed v. And so obviously for a wave function for the wave moving to the left at a speed v at a later time t, you will just change the negative sign in parentheses to a positive sign. So instead of x minus vt, you would have x plus vt for a wave moving to the left. Now let's write this formula in a slightly different format. So let's say that the wave travels through a displacement delta x equal to one wavelength lambda in a time interval delta t equal to one period t. So we will see that the wave speed and the wavelength and period are all related by an expression given by v equals delta x over delta t, which can be written as lambda over t, or which is also equal to lambda over t. So if we substitute this expression into the wave function above, we have y of xt now equal to a sine, and we got again our 2 pi, and we shall put in parentheses x divided by lambda minus t divided by uppercase T for the period. So by writing the wave function this way, we are showing the periodic nature of the wave function. So let's write wave function y of xt equals y now, so that we don't have to keep writing y of xt all the time. With this in mind, we can see that at some time t, the wave function y has the same value at the positions x, x plus lambda, x plus 2 lambda, and so on. And in addition, at any given position x, the value of y is the same at times t, t plus uppercase T, t plus 2 uppercase t, and so on. Now let's express the wave function in a more convenient form by defining two other quantities, which are the angular wave number k, and this is sometimes called a wave number, and the angular frequency omega. So we will say the wave number k is equal to 2 pi divided by lambda, and the angular frequency, so this is our wave number, and our angular frequency omega is equal to 2 pi over t, which we can also write as 2 pi f. So this is our angular frequency. So with these new definitions in mind, we can rewrite the wave function as y equals a sine of kx minus omega t. So this means that we can express the wave speed v as equal to omega over k, or we can write v equals lambda f. The wave function as written above assumes that the y position of an element of the medium is equal to 0 at x equal to 0 and at t equal to 0. If this is not the case, then we can generally write the wave function as y equals a sine kx minus omega t plus phi, where phi is the phase constant. Let's see how all this works in an example, and I'll just write the example out for you. So I'll read it out for you. A sinusoidal wave traveling in the positive x direction has an amplitude of 15 centimeters and a wavelength of 40 centimeters and a frequency of 8 hertz. The vertical position of an element of the medium at t equal to 0 and x equal to 0 is also 15 centimeters as shown in the figure. A. Find the wave number k, period t, angular frequency omega, and speed v of the wave. And B. Determine the phase constant phi and write a general expression for the wave function. Let's start off by drawing a diagram of the wave. This is x and that's y. And so the wave shown is this wave here. So we know the wavelength is 40 centimeters. The amplitude A is 15 centimeters. So that's the distance from here to here. And before we get into the solution, let's write out the quantities that we know. So wavelength is 40 centimeters, amplitude is 15 centimeters, frequency is 8 hertz. Okay, so now we can start our solution. So for A, first thing is to find the wave number. The formula for wave number is given by k equals 2 pi divided by lambda. And we can say this is equal to 2 pi radians divided by the wavelength of 15 centimeters. Sorry, the wavelength is 40 centimeters. So we can say this is equal to 2 pi radians over the wavelength of 40 centimeters, which we can write as 40 cm. So we can write this as 0.157 radians per centimeter. And then we can also find the period t. The period t is an inverse of the frequency. So we can say that's 1 over 8, which can be written as 0.125 seconds. Next is angular frequency, omega, and this is equal to 2 pi times f. So we can say omega is equal to 2 pi times 8 hertz, which is 8 per second. The hertz is just 1 over time, so it's 8 per second, and that can be written as 50 radians, no, actually 50.3 radians per second. And the speed of the wave, v, is equal to lambda times f. So we have 40 centimeters, multiply that by the frequency of 8 hertz, which is 8 per second, and that gives us 320 centimeters per second. Part B is to determine the phase constant phi and write a general expression for the wave. So we know that the amplitude is 15 centimeters, and we are saying that y is equal to 15 centimeters at x equal to 0 and t equal to 0. So this was given to us in the question where we were told that the vertical position of the wave was 15 centimeters at x equals 0 and at t equals 0. So if we take the wave function where the vertical position is 15 centimeters, the amplitude is 15 centimeters, and the sine of kx minus omega t plus phi is known, then we can say that since x is equal to 0, then we shall have k times 0 minus the angular frequency omega times t, which is 0 plus phi. So this is our wave function for the quantities that we were given. And so with this in mind, we can see that 15 centimeters for the position of the wave, or the y position of the wave, at an amplitude of 15 centimeters sine phi, because k is now gone. K times 0 is 0 and omega times 0 is 0, so those go away. So in order for this to work, we require that the sine phi should be equal to 1, which means phi is 90 degrees, or pi over 2, because we know sine 90 is equal to 1. So that directly tells us what phi is. So we can now write our wave expression. So we shall write y equals a. First of all, let's just write it in general form, and then we'll plug in the quantities we know. Y is equal to a sine kx minus omega t plus phi. And so we can write y equals 15 sine k, and we know k is equal to, let's see, 0.157, multiply that by x. Angular frequency is 50.3, multiply that by t, plus phi, which is pi over 2. We can also write this in a slightly different form using the cosine if we recognize that we can use the trigonometric identities to show that sine kx minus omega t plus pi over 2 is equal to cosine kx minus omega t. So what this is telling us is that when we shift the sine by 90 degrees, it becomes a cosine. That's what this is telling us. So we can now write our formula for the wave function y to be equal to 15 cosine 0.157x minus 50.3t. So we've transformed the sine into a cosine by shifting. Since it is shifted by 90 degrees, we can call it a cosine. Now let's look at something slightly different. Let's look at the motion of a point P on the string. So again, we have our wave y equals a sine kx minus omega t plus phi. If we assume that there is no phase difference, we can say that y equals a sine kx minus omega t. So we can draw this below. This is x again, and that's y. And so we have our traveling wave, which is a sinusoidal wave. And we can look at a point P on that wave. The point P moves only vertically. So its x coordinate remains constant. So in this case, transverse speed v subscript y, make sure you don't confuse that with the wave speed that we talked about previously, and the transverse acceleration a subscript y of elements of the string, or let's say elements of the wave. And we just note that the wave is on a string, so the medium through which the waves are propagating is a string. To find the transverse speed, we just take a derivative of the wave. Vy is equal to minus omega a cosine kx minus omega t. And similarly, transverse acceleration a subscript y is given by ay, which is a derivative of v subscript y dt, again for x equals constant. So we can write a subscript y equals minus omega squared a. We are back to sine again, so sine kx minus omega t. So with these two expressions for the acceleration a subscript y and the speed v subscript y of a point P, which is moving in the transverse direction on a wave. The wave has a wave function that we've been using all along, and this wave is generated on a string. So when we look at it that way, we can see that the acceleration, or let's start with the velocity v subscript y, we wrote as minus omega a cosine kx minus omega t, and a subscript y was minus omega squared a sine kx minus omega t. And so we can find the maximum speed, maximum transverse speed for the point P, or any point obviously on the wave medium. And this Vy max can be written as omega a. And the reason why this works is that we want kx minus omega t to be equal to 0, because cosine 0 is equal to 1. So by doing it this way, we can say the maximum speed Vy max in the transverse direction is omega a. And we are interested in the absolute values. So this is absolute value, so the negative sign goes away. The same way, the maximum acceleration in the transverse direction is equal to omega squared a, where again absolute value is used. And finally, we will note that the maximum velocity or maximum transverse speed v subscript y occurs at y equals 0, while the maximum transverse acceleration a subscript y occurs ay max, obviously. Let's put a max there and a max here. And this occurs when y is equal to plus minus a. So we shall stop here and continue next time with the speed of waves on a string.